Welcome back, guys. Today we'll look at paper 1 variant 13 of the May-June 2023 series. Now, as always, this video is supposed to be in addition to the mark scheme, because while I might give 2 or 3 answers, of course the mark scheme might give 4 or 5, and the mark scheme is the official source. However, I know some people, they look at the mark scheme, right, maybe they don't understand why this is given as the correct answer. So the whole purpose of these videos is that, well, not only will I try to give my answer, but I'll also explain why I'm giving this answer. Right, but as always, this video might go on quite a long time, so I'd recommend probably watch at 1.25 or 1.5 times the speed. Right, so the first one, computer stored data as binary. The binary number, okay, this is stored. Convert the binary number to denary. Right, so if you've seen some of the other videos, and hopefully you sort of learn how to do this yourself. So here then, we just want to write out the positional values. So we've got 1 and then 2. Then 4, alright, 8, 16, alright, 32, 64, and then 1 to 8. So here we've just got 8 bits. So I guess if we want to add that, well, we've got 128 plus 32, right, that's going to be 160. Right, then we've got plus 8, so 168, okay, plus 4, 172, and then, plus 2, right, so that should be, 174. And I would say, in the exam, okay, just double check your answer here, because it is easy to make a, silly little mistake. Right, then we want to convert the binary number to hexadecimal. So as I've said before, because there's a relationship, right, if we think 2 to the power of 4 equals 16, so what that means is that, well, 4 bits are going to be equal to 1 hexadecimal, 1 hexadecimal character, or 1 hexadecimal digit. So if we just zoom in, well, I said the first one is, let me just write it again here. So the first 4 bits are going to be this. So if we think, well, this is going to be 8 plus 2, right, that's 10. Now in hexadecimal, right, 10 is going to be A. Then here, if we look at the next 4 bits, right, 1110, well, that's going to be 14. Okay, because, well, 4 ones is 15. And then here, if we don't have this 1, right, that's going to be 14. 8 plus 4 plus 2. Now 15 in hex is going to be F. So that means 14 in hex is therefore going to be E. Right, and of course, if you need to, you can write these down. So of course, A is going to be 10, B is going to be 11, C is going to be 12, D 13, E 14, F 15. Right, a logical shift of 3 places performed on the binary number. Give the 8-bit binary number that would be stored after this logical shift. Okay, so yeah, let me just write it out again here, because I've kind of scribbled all over that. Right, so if we're shifting 3 places to the left, then basically, these first 3, right, they're going to get shifted out. So, we can then kind of write down these ones, and then we just want to think, well, then we're going to shift in 3 zeros from the right. So yeah, basically just this. Okay, yeah, so hopefully that makes sense. Right, tick 1 box to show which statement is true about the impact the logical binary shift left would have on the binary number. Right, so usually if we're shifting left by 1 position, right, we're going to double. If we're shifting left by 2 positions, right, it's going to multiply by 4. Shifting left by 3 positions, right, it's going to multiply by 8. So effectively, the number of positions we're shifting left is going to multiply by this amount. Likewise, if we're shifting right, well, then it's just going to, right, then it's going to half. Right, if we're shifting right by 2, it's going to quarter. Shifting right by 3, right, it's going to, sort of divide by 8. But well, so let's go through this. So here it says the least significant bits are lost. Well, this is going to be false, because when it says, well, least significant bit, the least significant bit is going to be the rightmost, okay, or the bit with the smallest value. And of course here when it says least significant bits, well, that would be talking about, I guess these 3. But here that's not true. So B, well, the most significant bits are lost. Right, in this case this will be true, because what this is saying, well, it's saying the 3 leftmost bits, the 3 bits with the highest value, right, so again, 1 to 8, 64, 32, right, they're going to be lost because, well, they're shifted out. So, I think this one is probably correct, but, let's read the next 2 just in case. Right, the number has been divided by 6. Well, so yeah, usually it's going to be divided by 8, however, because we've lost some of these bits, we're actually going to get the wrong answer. So yeah, it's probably not been divided by 6. And while the number stays the same, I mean, yeah, that's going to be false because, well, we've gone from 101, right, to this. So yeah, in this case, right, B must be true. Right, so then we just want to add these numbers. Okay, so let's write them here. Right, then the next one. Okay, so just adding these then, well, 0 plus 1, that's going to be 1, right? I mean, yeah, these next three are easy, right? So 1 plus 0, 1 plus 0, 1 plus 0. I mean, in fact, right, so all of these are easy. Yeah, so 0 plus 1, right, that's 1. Okay, all right, so here we do actually have two 1s. So in this case, well, right, 1 plus 1, that's going to equal 0, and then carry the 1. Now, I've explained this before, but yeah, maybe people didn't see those videos. I mean, the way that works is because if we think, right, 1 plus 1 in binary, well, that's, of course, that's going to equal 2, but 2 in binary is 1, 0. So if we just write that here, okay, let's say 1 plus 1, you know, writing it in this vertical format, well, what we're saying is the sum is going to be 0, okay, but then we carry the 1. And if you look at that, of course, 2 is going to be 1, 0, yeah, if we look here. And I mean, that's literally what we've got, okay, because we've got a 1 in this, you know, 2's position. And then obviously a 0 here in this 1's position. Likewise, you know, this also works if we do 1 plus 1 plus 1, right? That should equal, well, 1, 1, right? Because 1, 1 is 3. So here we say, yeah, the sum is going to be 1 and then the carry is 1. So if we look at that, okay, yeah, 1 and then 1. All right, so that's going to be the 3. So, well, yeah, looking at this then, so then again, we've got 1 plus 1 plus 0. All right, so again, that's going to be 0, carry the 1. 1, 1, 0, again, 0, and then carry the 1. And I think here, I mean, let's write 1, okay, but this is going to be overflow. So because it's overflowing, right, I'm just going to write that in brackets. Yeah, just to show that that's, you know, not actually included in the final answer. However, I think usually they do want you to write this overflow, right, and yeah, just put it in brackets. Then it says the denary number 301 needs to be stored, and we want to calculate the least number of bits that can be used to store the denary number 301. So for this then, I mean, basically we can just write down the, you know, binary positional values. So if we start, well, 2 to the power of 0, that's going to be 1. Of course, then we go, well, 2 to the power of 1 is going to be 2, right, then 4, yeah, 8 is 16, 32, right, 64, and then 1 to 8. Now, I mean, you've got to think, well, when do we know, like, when to stop? And what you should know is that whatever position you take, so for example, let's take this 8 position, well, all of the bits to the right of that, so effectively, right, 4, 2, 1, they're going to add up to, well, let's say n minus 1, right? So if we're saying here n is 8, then all of the bits to the right of that are then going to add up to 7. Because, yeah, we can see 4 plus 2 plus 1. Likewise, of course, if we take 64, right, all of the bits to the right of that are going to add up to 63. So what that means, like, if we're on this 1 to 8, well, effectively then we have 128, and then all of the bits to the right of that are going to be 127. So yeah, 128 plus 127, right, with 1 byte, that means the biggest number we can represent is 255. So that means we then have to go to the next one, right, which is 256. So this is always the thing, and well, let's say the next one is 512. So whatever number we need to represent, we always have to go, like, in the middle. So let's say we wanted to represent 200. Well, 200 is between 128 and 256. So therefore, to represent 200, yeah, we're going to have to be here. Well, okay, sorry. So yeah, because 200 is in between, right? Then it means we're going to need, you know, this, right? So 8 bits. Likewise, if we want to represent 301, well, 301 is here in this position. So yeah, that means we need, well, 256. Which is going to be, what, 9 bits. Right, now, if you want to be kind of more mathematical about this, because let's say, I don't know, if someone says, you know, you want to represent like 10,587 billion, right, whatever. I mean, you wouldn't really want to be doing this manually. So to actually do this, you can actually just use, well, log base 2. And, well, that's going to be log base 2 of n. Okay, and then n is, well, yeah, n is going to be the number we're trying to represent. However, this will get you a decimal, so then what you want to do, well, you want to use the ceiling function, which I think in maths they often represent with these kind of like square brackets. But notice how it's a square bracket with the top, okay, but this square bracket, it doesn't have the bottom. So what the ceiling function does, right, this means it will always round up. Now, alternatively, you can have the floor function, which is basically, well, it's just the opposite. So you have the the bottom kind of lines, right, but you don't have the lines at the top. And the floor function will always round down. And I do just have an example here. So let's say if we do, well, log base 2 of 15, and if you've got a scientific calculator, you can try this. What it's saying here, the answer is 3.9, right? Then if we round that up, that's going to mean 4. And this makes sense, right? Because we're saying to represent 15, we need 4 bits. And if you think, well, 8 plus 4 plus 2 plus 1. Now, let's try with our example of 301. Right, 301 is saying 8.2, and again, remember we have to round up. Okay, so this will give us our answer of 9. Right, so the hexadecimal number A4D needs to be stored. Calculate the least number of bits, okay, that can be used to store hexadecimal, right, A4D. Right, so here, well, like I've said before, was it up here? Yeah, what we said then is that, well, one hexadecimal digit is going to be 4 bits. So this one's actually quite easy. We can just say, I think here we don't really need to show our workings. So here we can just say 12. Alright, because again, if we've got 3 hexadecimal digits, well, 3 hexadecimal digits, and right, each digit is 4. Each digit is 4 bits. Right, 2, a library has a self-checkout system that allows customers to register books that they want to borrow. Right, the self-checkout system has a CPU, central processing unit. The CPU has 2 cores. State the purpose of a core in the CPU. Right, so I do have another diagram for this. And yeah, this one is a little bit blurry. Now, what you can say is that, well, here, the processor can be multi-core. Now, each core will have its own set of registers, right? So its own program counter, its own, right, MAR, MDR, CIR. Right, also its own, ALU, right, arithmetic logic unit. Things like status registers. And then each core can execute instructions independently, right, and also simultaneously. Simultaneously, with the other cores. So in this system, right, if we've got 4 cores, then effectively, the processors, right, 2 processors here, they can be executing 4 instructions at the same time, because of course, one instruction can execute on each core, with 4 cores, all right. So, I think here then what we can say is, well, a core will just be used to execute instruction. So let's say maybe a component. Let's say a component inside the CPU, right, used to execute instructions. Execute. And then, we can maybe give more details. So let's just say each core. Right, each core has its own set of registers, ALU, right, etc. Right, so each core has its own registers. Let's go ALU, and then just etc. Right, the CPU is replaced with one that has 4 cores. Explain the effect this has on performance of the self-checkout system. Right, so here then we can say, well, the performance will increase. Let's say, right, performance will increase. Right, and we can say, well, because each core can execute instructions sort of independently. Because each core can execute instructions independently. And then let's say like hence, right? So hence this provides. You can say parallelism or simultaneous execution. Let's use sort of both of those words. Let's say parallel / simultaneous execution. Let's say simultaneous execution of instructions. Maybe like across all cores. So I think that should be fine. Right, CPU contains registers and buses. Describe the role of a register in a CPU. So a register, well, that's going to be, let's say, small fast access memory that's close to the CPU. Right, yeah, fast access memory. I mean, well, yeah, let's say like inside each core. Let's say, I don't know, maybe can be used, or I mean, well, we can just say examples maybe. Yeah, okay, I mean, let's go can be used. Right, can be used, right, to e.g. And I mean, let's give some examples. So let's say store, I mean, so if we're talking about the PC, right, the program counter, let's say store the address of the next instruction. Yeah, and I mean, I think, you know, you could also mention what the MAR, MDR, but I mean, let's probably mention the accumulator because, you know, that's quite important, you know, just to store the result. Right, so to store the address of the next instruction, let's say, yes, store the result of, you know, arithmetic or logic operations. Right, so store the result of, yeah, arithmetic, right, I mean, let's just say I mean, what, or and, or maybe just slash, right, logic instructions, or yeah, operations. Right, I think that's okay. Identify one bus that can be found in the CPU and explain its purpose in the fetch decode execute cycle. Okay, so I mean, maybe, yeah, I think probably the easiest one might be the data bus. So all right, let's just go here, right, data bus. And what we can say, well, the data bus is going to be used to transfer data, let's say, between memory, right, and the CPU. And this can be either, you know, writing data, right, from the CPU, right, into memory, yeah, or reading data, you know, from memory, yeah, into the CPU. Yeah, so let's say, yeah, used to transfer data. So I mean, let's put in brackets, right, transfer. So that's going to be, well, read and write. Yeah, let's say, right, between the CPU. Right, and then let's say, yeah, and memory. I mean, so for memory, I mean, so we can give different examples, right? So we can say registers. Yeah, and then, I mean, we can also say, for example, cache. You know, we can say like main memory, right? So RAM. Yeah, so I think that should be fine. Now, let's say if you wanted to mention the address bus. I mean, well, of course, the address bus is used to transfer addresses. So, for example, if you're doing like, well, I mean, let's say you're wanting to read data, basically what's going to happen is, well, the address that you're trying to read from will be sent along the address bus. And I mean, well, yeah, maybe let's just sort of do this. So let's say this is the CPU, and then, I don't know, maybe outside, I mean, let's say this is, for example, level 3 cache. Yeah, I mean, here, let's say we've got, you know, main memory. Right, so main memory is just RAM. Of course, you know, you've also got the registers inside. So I mean, let's try and just draw this address bus. So let's say you send some address, I mean, I don't know, like, I mean, of course, this is going to be in binary, but let's say it's just the address, like 1,000. Now, if, for example, we say that the registers have the addresses, I don't know, maybe 0 to 100, maybe the cache has the addresses, well, let's say 101 until, you know, 9999. I mean, yeah, I don't know, let's make that bigger. And let's say this one has the addresses, you know, 1,000 until like 1 million. Or yeah, probably, you know, billions, to be honest. So what's going to happen then is, well, if you're doing a read signal, so if you're trying to read data, basically this address will be sent along the address bus, and then like each, let's say each component will then check this address to check that if this, let's say to check that if it contains this address, basically. So when we say the first one, the registers, well, it's going to think, right, this, you know, 10,005, right, this is not in its range of, you know, well, 0 to 100. So basically the signal is going to carry on the address bus. You know, then it's going to arrive at the cache. Well, so the cache, right, you know, this is its range of addresses. Again, of course, well, this 10,005, right, this is not in this range. But then obviously when it gets to main memory, right, well then it is going to be in this range. So what the main memory will do is it will then think, well, now I need to read the data, from this address, 10,005. Of course, it's going to load that data, right, and then it's going to send that data back. And of course, that data is then going to be sent back, right, on the data bus. So yeah, you can mention that, and of course that's going to work for, well, reading data, but also writing data. So okay, so my computer just shut down there, and I think probably overheating. But what I was saying is that if you want to write data, then well, you're going to send the address that you're writing to on the address bus. You're going to send the data that you're writing, on the data bus. And then basically when the component that has that address receives it, right, then it's just going to write that data. Obviously, to that particular address. And then I guess the final one, well, the control bus, I mean, really that's just going to be used for the control signals. So you can say things like timing signals, right, when the clock pulses. I think things like interrupts can also be sent on the control bus. Right, so the next one, the self-checkout system allows the user to input their library membership number, give 2 appropriate input devices that would allow the user to do this. Right, so I think here, because it mentions number, I mean, of course, we could say keyboard, but I think here, I mean, we can really say keypad. Maybe keypad or numpad. And I mean, what a keypad is, think of like an ATM machine, right, where like rather than having the letters, okay, you literally just have the numbers. Of course, 4, 5, 6, 7, 8, 9. And then, probably like a 0 at the bottom usually. Right, and then, I mean, let's say another one, we can probably just say touchscreen. Because I mean, basically you want something easy that they can use. Keyboard is probably not that convenient, because, I don't know, maybe people can unplug it or something. Whereas, a touchscreen is built in. People can't really, move it or anything like that. Right, the self-checkout system uses a monitor to display information about the book. Users who are blind also need to use the self-checkout system. Give an appropriate output device that would allow a blind user to be given this information. So, I mean, obviously you think, well, if they're blind, then it's going to need to be audio. So, I mean, you could mention headphones, but I think for me, I'm just going to say a speaker. Because, the thing with headphones is, well, if they're blind, right, I mean, somehow they need to be able to actually, pick up the headphones, which, that could be a bit of a problem. Whereas at least a speaker, right, it's just going to play the audio out loud. They don't have to pick anything up. Right, self-checkout system uses 2 types of primary storage. Circle 2 types of primary storage that would be used in this system. Okay, so actually, I mean, primary storage, there are only 2 types, right? So that's going to be, RAM, right, random access memory, and then also, ROM, okay, read-only memory. And if we just think, well, the definition of primary storage is that, it's going to be storage that can be directly accessed by the CPU. Whereas, let's say, for example, if you want to load something from the hard drive, so let's just do this, right? So here is the CPU. Here, I mean, let's just say RAM, right, main memory or RAM. And let's say here, this is, the hard drive or SSD, basically secondary storage. Well, you can't have it where the data is directly loaded into the CPU. Right, what needs to happen is, first the data is loaded into RAM, and then, from RAM, then the data is, loaded into the CPU. So that's why we say, primary storage is primary, because again, it can be accessed directly by the CPU, but secondary storage is, secondary, because obviously, basically it can't be accessed directly by the CPU. Right, there's going to be, 2 stages. If we just look at these, compact disc CD, right, obviously that's going to be optical storage. Again, DVD, right, also optical storage. So optical just means we're using light lasers, and that's usually going to work with, pits and LANs. Also, you can say different levels of reflectivity, based on some, chemical properties of the surface of the, DVD or Blu-ray. Hard disk drive, obviously that's going to be magnetic storage, and then USB, right, that's going to be solid state storage. Similar to, an SSD, right, solid state. Self-checkout system is linked to a stock control system that's updated every time a book is borrowed from the library. A microprocessor is used in the stock control system to update the stock. Explain the role of the microprocessor in the system and how it's used to update the stock when a book is borrowed. Okay, so what you can think then, obviously there's going to be a database, and let's say each book is going to have some ID, right? Maybe the ISBN number. And then, right, when someone takes out a book or when someone borrows a book, of course, the ID in that data, well, not the ID, but you know the stock number associated with that ID is going to be decremented by 1, because I mean, let's say you have 10 copies of that book. Obviously, when someone takes out that, right, then it's going to decrease to 9. However, also when they return the book, right, then it's going to increase again back to 10. And yeah, we can also. Yeah, I mean, I think we probably don't have to mention any kind of error checks here, because again, if the book is in the library, well, then it means the stock should be bigger than 1, or well, bigger than 0, right, greater than or equal to 1 in that case. So yeah, let's try and explain that. So let's say, yeah, I don't know, maybe there will be a database. Or let's say there will be a database which contains. I mean, let's say, I don't know, maybe like an ID number for each book. Right, yeah, and its stock level. Or I mean, do we have to mention anything? Maybe the book will be scanned or something? No, I mean, probably not. So let's say, right, let's say when a book is borrowed. Okay, all right, hang on. Right, so when a book is borrowed, we can say, right, the microprocessor will, I mean, basically it will create a database query to, decrement the number of stock. So yeah, let's say the microprocessor will maybe perform, or yeah, just send, let's say send a query to the database. Right, send a query to the database to reduce the, yeah, I don't know, let's say the stock level for that book by 1. Yeah, I mean, I think that's fine. And then, I mean, here it does mention when it's borrowed, but I think we can also mention when it's returned. So let's say, yeah, when the book is returned. Right, yeah, let's say I mean, basically the same, right? So the microprocessor will send a signal to the database, and then, well, rather than saying reduce, we just say increase the stock level by 1. Yeah, that should be fine. And I mean, in terms of like the SQL query, now for IG, right, this is not actually required. For A level it is. But if people do want to see, how you do this in SQL, I mean, basically you just go update. I mean, let's call it book. And then what you do is, well, you just go set. So you go maybe set. I mean, let's call it like I don't know, let's call it SL, or just if I say SL stock level, and that'll be equal to SL plus 1, right? And then we just need a where condition. So similar, just like when we go, select, right, then the columns, yeah, from, then the table name, and then we have where. When we have an update, we also have where. And let's go, right, where ID equals, and I don't know, yeah, 1, 2, like 1, 2, 3, 4 or something, just the ID of the book. Then of course, well, I mean, well, this is going to be when they return it. I guess when they borrow the book, right, it's going to be -1. Right, 5 network terms or definitions given in the table. Complete the table. Okay, right. So just fill in the blank. Right. So router. I mean, if we think about a router, yeah. Do I have space to draw this? So if, for example, let's say we've got a client, right, and well, then we've got the server. You're going to have routers kind of throughout the whole network, and I mean, let's say the file or the web page, right, whatever it is. That's going to be broken down into packets, right? And of course, some of these packets can be sent along, maybe this route. But yes, some of the packets can, maybe be sent along, a different route. And then when they get, to the, server, or just the, let's say the receiver, because of course, right, they're also going to be sent back as well. So yeah, when they get to the destination, well, maybe the packets arrive in the wrong order, like, 312. Okay, so in that case, they're then going to have to be reordered, right, into like 1, 2, 3. Also, let's say something like, I don't know, we get the packets 3, and we also get the packets 1, okay, but we don't get packet 2. Well, then there's going to have to be a retransmission, right? So yeah, that's also going to be handled, by the packet number right in the in the packet header. So yeah, I mean, basically the definition of a router. Well, it's going to use its routing table. I mean, the routing table, I think, just to recap this, the routing table is just going to have a list of like IP ranges, and then it's going to have like the next destination we can send it to. So let's say if our IP range is, I don't know, like 0 until let's say 100, right, dot dot dot. So when I say 0, I mean like an IP like 0.0.0.0, right, to an IP of, let's say, well, 100, right, dot 255.255.255. So let's say anything in this, could be sent to, I don't know, the router with the address, maybe 10.10.10. Yeah, something like that. Now, yeah, sorry, that should be a 10 there. Now, we can have something else, maybe IP addresses in the range like 101, to, let's say 200. Right, they can then be sent to, the like a different router. Right, so what a routing table is going to do, I mean, it's just going to have the range of IP addresses, and then, the let's say the router to send it to, if it's within, right, a given range. So yeah, let's sort of say that, let's say maybe determines, right, let's say determines the next hop, and like in brackets we can just say router, although, the hop could also be like the end device, or yeah, a switch or something. Right, determines the next hop to forward packets onto. Right, and it's going to do this based on its routing table. And again, if something like the routing table doesn't make sense, if you want to know about this, well, just search it online. And I think the book also has a simple definition. Right, the next one, this address is assigned by the network and is used to identify a device on a network. Okay, right, so yeah, this will then just be an IP address because it's assigned by the network. And specifically, we can say it's assigned by the DHCP server. Right, so, well, I mean, okay, alright, so if it's dynamic, okay, if it's a dynamic IP address, well then, yeah, the dynamic host control protocol is going to be assigned, right, using the DHCP server. And for home routers, okay, home routers actually have a DHCP server built in. Just like home routers also act as a DNS, right? They're also a switch. They're also a gateway. Yeah, I mean, home routers, right? They have a lot of functionality built in, because basically, like, people don't want 5 different devices. You wouldn't want to have a router and a DNS server and a DHCP server, and a switch, right? I mean, for let's say for normal, home or office uses, of course, you want everything built into one device. But yeah, I mean, obviously, if it's static, well, then it's going to be assigned by the network administrator. But I think here, well, again, yeah, let's just say IP address. And I mean, IP, right, that stands for Internet Protocol. Yeah, that's what it stands for. Right, network interface card, I mean, basically this allows a device to connect to the network. So maybe let's say that, right, allows device. Yeah, let's say, right, to connect and communicate over the network. Right, yeah, so to connect, right, connect and communicate over a network. Right, then the last, well, actually no, not the last one, 2 more. This address is assigned by the manufacturer and is used to uniquely identify the device. Right, so the thing that's assigned by the manufacturer, that's going to be the MAC address. And MAC, right, if you don't know, well, that's, right, media access control, or yeah, media access controller. And well, if we think of the MAC address again, you're going to have well, it's going to be 12 hex digits, and the first 6 hex digits, right, from the manufacturer, and they, well, basically they represent both the manufacturer and the, the specific model, because maybe you have like I don't know, maybe you have something like whatever, manufacturer of a router, but you have obviously different models, from that same manufacturer. Right, then the last 6 hex digits are going to be the ones that are, unique for that device. Right, the last one, this can be hardware or software based and filters traffic coming into and out of a network. Right, so this then is just going to be a firewall. Because what a firewall does, I mean, let's do a quick diagram. Again, let's say you've got the client, you've got the server. So the firewall is just going to sit in the middle, and then any traffic, let's say any outgoing traffic is going to hit the firewall. And then the firewall will think, well, is this traffic legitimate? And for example, I mean, let's say, for example, a school might have this. Right now, let's say you're trying to communicate with an IP address, and let's say this IP address is for, I don't know, like youtube.com. Now, let's say the school doesn't want people, watching YouTube. So what they would say is, well, anything that's going to, the IP address of youtube.com, basically we're just going to block that traffic. And of course, this can also be blocked, not only based on the IP address, but things like port numbers, right, the protocols. For example, like maybe you don't want, let's say like, I don't know, maybe FTP traffic, right, so file transfer protocol, because that could be some like malicious request where someone is trying to actually send FTP traffic, out of the network. And I mean, this is also going to work for incoming traffic. So I don't know, if we've got some traffic from some IP that we've blacklisted, right, because maybe this IP is trying to, DDoS, or just, denial of service, or distribute denial of service. Right, in that case, again, we can also block them. Likewise, based on, right, the protocol, the port number, things like heuristics, right, so how much data they're sending. Right, next one, a program writes a computer program in a high-level language. Tick one box to show which statement is the benefit of writing a program in a high-level language instead of a low-level language. Right, so the program can directly manipulate the hardware. Well, this is false, right, because this is going to be low-level. Because in low-level, for example, you can, directly access registers, okay, things like that. Right, the program is machine independent. I mean, this should be true. Now, again, I'm going to read the others just in case. And the reason this is true is because, well, if you think about assembly, right, or machine code, I mean, that's going to be, processor independent. So, for example, you have some, let's say you have some, assembly or machine code for, say 64-bit computers. You have others for, 86. And like when it says 86, I mean, what that means is actually 32-bit computers. I can't actually remember why they call it 86. And then, for example, you've also got, ARM-based computers, right, other things. Or kind of ARM-based processors. And, each of these, they're going to have their own assembly language, which, of course, corresponds to, their own machine code instructions. But something like a high-level language, I mean, let's say, Java, Python, VB, well, you write that the same, and then it's going to get either, compiled or interpreted, and it should run on any system. Right, so program is more memory efficient. I mean, like usually no. In theory, in theory it's possible to kind of make a low-level language more memory efficient, because again, you can directly access the registers, right? You can do, bit manipulation. You just have more control. And well, likewise, the last one, program is quicker to execute. Well, in theory, a low level could be quicker because you have more control. You have less kind of like wastage of sort of unnecessary instructions. So it's going to be this one, right? However, honestly, these two, I mean, in real life, it's not necessarily true. Because in reality, a compiler can actually do a lot of optimizations. And probably the compiler can produce more optimized code than most people just writing random assembly. Unless you were some kind of expert in assembly. Right, so translators are used to translate high level so they can be processed by the computer. State what the high level language is translated into. Right, so you think the only thing that can be executed by the computer or the processor, that's going to be machine code. Obviously from high level, into literally, zeros and ones, binary. Right, one translator converts and executes the code line by line. Identify which type of translator would do this. Right, so again, well here it's saying obviously execute line 1, right, then line 2, then line 3. And it's kind of going to pause between each one, right? So that's going to be an interpreter. Yeah, and I mean, there's actually not many languages that are purely interpreted now, because even something like Python, I mean, Python is going to be partially compiled, partially interpreted. I mean, that's the same as Java. Yeah, things like JavaScript, right? That's also, well, just-in-time, compilation. So I mean, there's some simple like scripting language. I think maybe Bash. So if people are familiar with this kind of, like let's say in the terminal, right, you can do like Bash scripting, and I think maybe that's going to be interpreted. And so what this will do is, I'm not sure the syntax of this, but let's say we have some echo, right, and like echo is like print basically. So let's say we have echo ABC, right, on line 1, okay, right, ABC. Then, for example, let's say we have echo, I don't know, like 1, 2, right? But let's say here, okay, we don't have this, we don't have this kind of like closing quote, basically. So what's going to happen? Well, it's going to execute line 1, right? That's going to be successful. But then on line 2, it's just going to crash. So in this case, the output is just going to be ABC. But then if we look at the next one, right, one translator creates an error report displaying all the errors in the code before it can be executed. Right, well, this is going to be a compiler. So if, for example, we said this is a compiled language, well, then it's not even going to execute, right? It's going to tell us, error on line 2, no closing quote or something like that. So some people might think, well, that's kind of annoying, right? If there's one error, it's just going to not execute at all. But you can actually think that's actually kind of safer, in the regard that if something successfully compiles, well, there's going to be no syntax errors. And usually the compiler will also check for things like, let's say, data types, right? So it will make sure you're not doing anything like, I don't know, assigning a string into an integer variable, or yeah, something like that. So yeah, you can say a compiler is kind of safer in that regard, okay, because it's going to check for a lot of errors for you. Rather than one translator creates an executable file, right, identify the translator that would do this. Okay, I mean, so yeah, this is also going to be a compiler then. I mean, yeah, I mean, for this, you could also say an assembler as well. I mean, does it say we can use the same one twice? No, it doesn't say. But yeah, I mean, for this, you can say, well, a compiler or an assembler. Yeah, although the fact it says one translator, like I'd probably go with compiler because, yeah, I guess they're just more common. But an assembler, you think, well, that's going to go from assembly into machine code. Whereas, yeah, compiler goes from, well, a high-level language right into machine code. Right, so complete and annotate the diagram to demonstrate how packet switching is used to transmit data across the network, right, including the use of routers from device A to device B. I mean, I think this one I won't do because I've actually done this already here. So where was it? Okay, yeah, this one. So of course, well, this client, right, this is device A, yeah, the server, right, device B. So what we can say, maybe here, let's just go like packet 1. Let's say here, this can be packet 2. And then, well, we just want to annotate this. So let's say here we say packets, yeah, packets arrive out of order. And then this one here, I mean, let's kind of draw an arrow to this. Let's say, yeah, packets reordered. And then, I mean, here we can sort of maybe here we can just say, I don't know, like missing packet. And then let's say, yeah, will be retransmitted. Yeah, so I think that's going to be all you need for this one, really. Alright, so next one, 6. A student is writing a help guide about how to recognize and avoid the cybersecurity threat of pharming. Right, give 3 appropriate solutions he could include. Okay, so pharming, I mean, often you think, let's say you want to go to, I don't know, Google. Well, rather than going to, google.com, right, maybe it's like google1.com. So I think one thing you can say, well, it's going to be check the URL. Right, so check, okay, yeah, what's happening? Right, check URL for correct spelling. Yeah, I don't know, like correct spelling / correct address, I guess. I guess similarly, we can also say, I mean, check it's using HTTPS, right? So effectively, check for that green padlock. So yeah, or let's say, ensure connection. Right, ensure connection is using HTTPS. Yeah, I was going to say HTTPS protocol, but I guess the P is actually protocol. So I think, yeah, we don't need to mention that. And we can put in brackets, let's say, yeah, green padlock in browser. Right, and then I think the last one, sometimes this can be caused by, for example, malware on the computer, where, the malware is, let's say, modifying DNS records. Like, I think, for example, on Mac Linux, it's going to be in the, etc host file. I think Windows is something like maybe system Windows 32, and then it's going to be like ECT host file. But you can literally open this, right? So if you're on Windows, just type in, yeah, go on Google, type in how to see host file on Windows, and yeah, you can find this. And what that literally has is, I think first it's going to go the domain name. So let's just say like google.com. Right, and then you just have the IP address of that domain. So let's say here we just give it a fake IP address, like 123.123.123.123. And potentially the operating system will actually look at this host file, and then it will just use this IP address. Now in this case, right, this is actually a fake IP address. It's not the real IP address of Google. And to be honest, actually, I think now browsers, they actually don't just blindly trust this host file. Maybe 10 years ago they might have, right? So yeah, because I remember doing this. You could easily like play pranks on people, literally just by changing this text file. Yeah, however, nowadays, right, I think it's not quite as easy. But anyway, I think, well, let's say, yeah, I don't know, maybe frequently run. So let's say frequently run antivirus, or well, probably anti-malware. Yeah, maybe to check for, let's say to check for corrupt, or let's say check for infected programs. Right, infected programs, yeah, probably all corrupted files. Yeah, so I think that should be okay. And here, like, yeah, I'm trying to think if you could mention firewall. Because the thing is, like, if for example it trusts the DNS, then I think the firewall is probably not going to do anything. Yeah, unless the firewall is configured to kind of, I don't know. Maybe the firewall could like check the DNS against some other DNS record. But yeah, I think these are probably the safest ones to go with here. Right, so the student also wants to include information in the help guide about the use of social engineering as a cybersecurity threat. Right, okay, so describe what's meant by social engineering and include one example in your answer. So social engineering, this is basically just about tricking people. And the way you would trick people, for example, you could pretend to be some sort of authority. Or yeah, you just sort of play, I don't know, play some trick. Maybe, like maybe you have their personal information. And because you have their personal information, right, then you can, for example, impersonate the bank. Right, so let's say social engineering. Right, let's say it's the act, maybe of manipulating people, right, into performing, let's say, kind of unauthorized or so I think maybe let's say actions that can compromise their security. Yeah, right, that can compromise, right, their security. Yeah, and then maybe we can say, often by by taking advantage of their trusting nature or something. Taking advantage of their naivety slash maybe lack of experience or something. Let's say naivety, slash, I don't know, like lack of experience. And then, I think, trust as well. Right, and then for the example, I mean, one we can say is maybe you sort of phone someone pretending to be the bank, and let's imagine that, I don't know, maybe you know where this person lives, because, well, either you know them in real life, or potentially you've just found that information online, right? Because there's a lot of websites where you can type in people's name, and obviously it will give you the address. Likewise, maybe their data was in a data leak, and in that case, maybe you can see their address, their email, their phone number, right, all kinds of things. So let's try and mention this. Maybe say an example. Could be maybe a malicious, I don't know, maybe a malicious third party, or a malicious, threat actor. It could be a malicious threat actor, maybe impersonating a bank. Let's say, trying to get the user to transfer money or something. Or I don't know, maybe give over their password or transfer money. Get the user to or let's say reveal password. Okay, so reveal their password. Or initiate a transaction. And I mean, we could mention maybe could be more convincing, or could be convincing. If I don't know, if they know users' personal information. And let's say, for example, like email or address. Because, I mean, you imagine, right, if they're the bank, like, if they ring up, they could say, hello, Mr. Smith, right, whatever. Can you confirm you still live at the address, like, 123 High Street? Is your email still, I don't know, bsmith@gmail.com? So, like, if they're ringing, sort of giving the user all of this personal information, well, then, of course, the user will think, well, if they know all of this personal information, then of course they're going to sort of trust that it is actually the bank, rather than just some like random hacker. So this shouldn't include information about security of access levels, or solution of access levels. Describe what is meant by access levels. So I mean, basically this is like, let's say if you have files, and I mean you can do this on Windows or Mac, whatever you've got. And for example, if you right click on the file, you're often going to have permissions, and you'll have different users, and of course different users can have different permissions. So for example, if you go into some of the system files, well, you'll have to be an administrator in order to modify those files. And you can say some files are going to have read permissions, but they won't have write permissions, or they won't let you create a folder or something like that. So let's say maybe different users. Different users can have different permissions. Let's give an example. So e.g. administrators. Administrators. So let's say administrators might have full privileges. Privileges. And then we can give in brackets. I mean, let's say I don't know, like read, write. I don't know, maybe make new folder. Alright, let's say etc. but let's say, but regular users might have a limited subset of those. Regular users, might might have a limited subset of those. Yeah, I mean, I think that should be okay. And then, I mean, I don't know, like, you could mention that I guess they would need a password, or in order to access their account. Right, so maybe a password, / authentication method. Because, I mean, obviously, well, some cases it could be a password, but other cases maybe it might be some biometric thing, like, facial recognition. It could be some, hardware, some sort of, USB key or something. Let's say to access the account. Maybe to access the, maybe to access the different accounts, or different account levels. So I mean, I think that should be enough for 3, right, hopefully. The rule-based and the inference engine are 2 components of an expert system. Identify the other 2 components of an expert system. So I'm just going to draw the example in the book again. So here, first you're going to have like the person. The person is then going to, they're going to communicate with the UI, right, the user interface. This one they don't tend to include in the mark schemes, but I'm going to write it anyway. So here they have the explanation system, and then here they sort of have another box. So right here, in this one they're going to have the rules base, in fact, I think on top let's have the knowledge base. Right, then here let's have the rules base. And then, I mean, we can also have another arrow, and let's say here, this is going to be the inference engine, right, so the IE. So just to recap, I mean, the way this works, again, using the example in the book, right, they're classifying dogs, or classifying animals. So, I mean, let's say, right, you have a list of rules, and, this rules can be, is it a, you say, like, right, is it a mammal, does it have 2 legs, can it swim, can it fly, right, etc. So that's going to be in the rules base. The knowledge base, that just has a list of facts. So for example, a dog, a dog, I guess it probably is a mammal. I guess you say, a dog has hair, or fur, right? A dog has 4 legs, right? All of these facts. And then basically the inference engine is going to use the rules base and the knowledge base in order to kind of derive the answer. Because, I mean, basically it can just ask questions, right? It can say, is it a mammal, right? Yes or no. And then, then it will go to the yes because it's a dog. And then it will ask, does it have 2 legs, right? And then it'll be no. Then it will basically it's just going to keep asking questions. And of course, eventually it's then going to get to an answer. So I think here then, I mean, the 2 other, I mean, let's say, user interface. And I mean, the user interface, of course, that's where the user can, type in their, I mean, I don't know, they can sort of type in their query, of course, but it's also going to display the answer, right, because there'll be like a screen or something. So the user interface and, so rules-based inference engine, so the other one then is the knowledge base. And again, like, sometimes they mention this explanation system, but it seems often they don't. Now, what the explanation system does, and I guess maybe sometimes they sort of include this as part of the inference engine, they sort of combine them together. But what the explanation system will do is, it's going to explain why it's, arrived at its conclusion, and also the sort of degree of probability, right, or the degree of certainty that it thinks its answer is correct. Because it can say, I think this is a dog, right, because, and then say, because, you said it's a mammal, right, it doesn't have 2 legs, but it does have 4 legs, it has fur, and, so on, right, I guess it can't fly, right, all of those, kind of rules and knowledge base. So here then we just want to explain the role of the rules base in an expert system. So let's say, the rules base, let's say it's going to have a list of rules. I guess maybe not a list, let's say a set, right, or you can say tree, but let's say, a set of rules. Let's say related, related to the scenario. maybe to the scenario the expert, the expert system is applied for. Yeah, maybe is designed for, I guess. Right, and then we can probably say the rules base will, well, you say, the knowledge base and the rules base will be used together by the inference engine in order to arrive at the kind of final solution. So yeah, maybe let's say the inference engine. Maybe the inference engine will, let's say, like apply the knowledge from the knowledge base. Right, so we'll apply the knowledge from the knowledge base. Right, I'm just going to say KB, right, KB knowledge base, right, to the rules, right, in the rules engine, or sorry, yeah, the rules base, right, I'm going to say RB, right, in order to arrive at its final, final conclusion, right, to, yeah, arrive, right, at its final conclusion. Okay, yeah, I think that's fine. Right, the next one, complete the statements about a distributed denial of service attack, right, DDoS. Right, so some of the terms will not be used and you should only use the term once. Right, so I think these, I always like to just read them first. So antivirus, okay, botnet, right, hacker, internet malware, secondary storage, spyware, web browser, web server, and website. Okay, so the attacker encourages people to download something onto their computer. Well, what they're going to be downloading, right, that's going to be malware. Right, this will turn each computer into a something, creating a network called a something. Right, I mean, so sometimes you can say, well, zombie, but I mean, here they only give us bot, right, so yeah, let's not say that, okay, and we'll just say bot. I mean, obviously, well, yeah, they're just the same, right, so zombie, bot, right, it's the same. Creating a network, well, called a botnet, so obviously a bot network. Right, when the attacker wants the DDoS to take place, repeated requests are simultaneously sent from the computers to a something. Right, well, this will be, to the web server. Right, this causes it to crash, meaning that users can no longer access the something that is stored on the hardware. Right, so here then this is just going to be the website. Now, I mean, yeah, in this case, I guess they're talking about, a website, right, web server. But equally, this could be like a database server. This could be, file server. But yeah, here obviously they're just talking specifically about web. I mean, let's just go through. I mean, antivirus, hopefully people should know. I mean, hacker, yeah, I think people know. I mean, malware, obviously that's the collective term for, all, collective term for all malware. And so, the types of malware, well, of course, you've got spyware, you've got virus, right, Trojans. Yeah, you got adware, ransomware, yeah, and I think worms. Right, that should be all of them. I mean, secondary storage, again, like we said, that's storage that can't be directly accessed by the CPU. Obviously, well, web browser, yeah, like Chrome, right, Firefox. Basically, it's going to send requests to the web server. Yeah, those requests are going to be sent back by, or sorry, yeah, the response will be sent back by the web server. And then the browser will then use that response in order to render the web page, and yeah, that's obviously going to be made by using the right HTML. Then also, well, obviously things like the images, the videos, right, the CSS, the JavaScript. And I mean, internet. Well, of course, people know what the internet is, but I mean, if you think, well, inter, right, that means kind of like many, or yes, kind of like connected. Right, and then, well, net is just network. So the internet is literally a collection of many networks, connected together, yeah, to form, kind of like a big network. And sometimes they do ask, like, what's the difference between, well, the internet and the, World Wide Web? So you say, well, the World Wide Web is just, the collection of web pages that are connected together via hyperlinks. And when we say hyperlinks, we just mean, right, links you can click on. So yeah, I mean, this is basically just using like HTTP, right? So just talking about the websites. Whereas the internet, I mean, that's kind of talking about everything. So yeah, I mean, one part is going to be like www, the World Wide Web, right? But the internet also includes things like email. The internet also includes, for example, other protocols like FTP, right? File transfer protocol. It's going to include things like, video streaming, phone calls, So like VoIP, right, voice over IP for phone calls. Yes, the internet just includes all of it, right? The World Wide Web is just the actual web pages. Right, so a device can be given an Internet Protocol IP address. This can be IP version 4 or IP version 6. Give one similarity between IP version 4 and IP version 6. Okay, so let's just say, let's say right, both. So both are used to uniquely identify a device. Right, and then I think other ones you can say, well, you say, right, both can be either public or private. So public means, well, basically it's going to be unique for the entire world. Whereas private, well, that only has to be unique for that particular network. So for example, if you're on like a home router, well, you can have a private IP address. For example, 192.168.0.1. And like on your network, you're the only person that has that. But for example, if you like go to school or your neighbor's place, well, there can be other people with that same private IP, because again, it's a private IP just for that network. And then actually to communicate with people, like I don't know, let's say here we've got, let's say this is like private IP1, right? Then you're going to have the router, and well, the router is going to have a public IP. Let's say this is router 2, right? Again, this is going to have another public IP. And let's say, this is another user, right? Let's call it private IP2. So let's say, the person, right, this user wants to send something to, this user in this network. Well, basically, of course, first it's going to send to this router. And, this router is just going to have the public IP. And so all the communication is just going to be done, right, using the, basically using the public IP of this router. Because, for example, like if P1 wants to send to, P2, well, P1 won't know P2's IP address, okay? But because this router has a public IP address, then, the router is then going to send it to, this router, using this public IP address. And then, right, when the router receives it, well, then the router can, of course, forward it on. So, that's kind of how it works, using, right, private and public IP addresses. Now, if you want to learn more about networking, there's actually some good channels. I think one is called like PowerCert. I think it's like PowerCert animated videos. So if you type in PowerCert animated videos on YouTube, and then search like, I don't know, maybe you want to learn about DNS, or you want to learn public private IPs. This channel has a lot of good stuff. There's also another one called CertBros, and again, they're also quite good. Right, so I think we said, so it's going to uniquely identify a device, right? They can both be public and private. They can also both be static and dynamic. So static means that it's fixed, right? It's kind of permanent. It's not really going to change, unless you request the, sort of manual, like rechange. Whereas dynamic, well, basically you're going to get a new IP address each time you log on, or each time you, turn on the device. And again, that's going to be assigned by the DHCP server, right? Or the router. Dynamic host control protocol. So I think that's going to be the main similarities. Right, then the differences, I think the difference is you can just talk about the formats. So I'm not going to write the whole thing, but basically IP version 4 is going to be 32 bits. IP version 8 is going to be 128 bits. So I think you can say that. You can also mention that IP version 4, where it's going to use 4 groups. And let's say 4 groups of let's say 4 groups of denary. 4 groups of denary numbers in the range 0 to 255. Whereas IP version 6, that's going to use 8 groups. It's going to be 8 groups of hexadecimal characters in the range. Hex is going to be 4 zeros, and then 4 Fs like this. And then I think you can also probably talk about the separators. So let's say IP version 4, right, is going to use the dot. Just the period or full stop separators, whereas IP version 6, right, it's going to use colon like this. So I think that's going to be the main differences. Okay. Right, so a web page is requested using an IP address. Identify the system that stores a database of uniform resource locators, URLs, and their corresponding IP address. Right, so this is just going to be DNS because, I think this is what, like I've mentioned before. where, for example, you just have, well, you basically have a table, or yeah, just like a dictionary, right, a mapping. So here it's going to be, let's say, the domain, right, and then right, what this is mapped to is going to be the IP. So, for example, let's say, I know row 1 we have just Google, so yeah, like google.com. Let's say that has the IP address 111, right, 222, maybe 11, right, 22. And then of course we can have another entry like, I don't know, yeah, like YouTube, right, and I don't know, maybe that's like, yeah, I know, 123, right, something, whatever. So here what you're doing, well, you're mapping the domain to the IP, because let's say you, right, or your web browser, it's just going to send a request, so it's going to say, right, what is the IP address of google.com, and then what the DNS server is going to do, well, then the DNS server is then going to respond, and it's going to say, well, yeah, here, right, this is the IP address. So yeah, that's kind of how that works. So let's say DNS, and then we'll just put in brackets, well, domain name system. Yeah, and I think, I mean, this S, you can use server, you can use system. Yeah, I think both are accepted. Right, identify the software that sends a request to the IP address to obtain the web page data. Right, so I mean, when it says the IP address, I mean, this is talking about the IP address of the web server, right? So basically, sending a request to the web server. So the thing that sends a request to the web server, right? Well, that's going to be the browser, or the web browser. And of course, this request is going to be, you know, an HTTP, right, or HTTPS request. Right, then I think, okay, wait, no, not the last question. Alright, so a computer has pages A, B, and C that are stored in RAM. Page D needs to be sent to RAM, but the RAM is full. Right, page B is not needed immediately. Right, explain how virtual memory can be used in this scenario. Okay, so if we just draw a diagram, right, explaining how this works. Let's say we've got, I don't know, I mean, right, so let's say we've got these pages we need, right, so we're A, B. Right, so A, B, C, and D, and I guess, like, if they're pages, right, they should be the same size. So let's say in RAM, right, maybe our RAM, we can only fit 3 of them. So let's say what we've got, A, B, and C. Right, so now then we've also got our secondary storage. Now this could be a hard drive, it could be SSD, yeah, it doesn't matter. Now basically we're going to allocate some of this secondary storage. So if it's a hard drive, let's just draw this part. Right, so this can be allocated as being, you know, virtual memory. I think often, yeah, on a typical computer you might get 16 gigabytes of virtual memory, maybe 16 to 24, right, something like that. So what's going to happen? Well, here, because we don't need B, we can temporarily put this B, you know, on the hard drive, or yeah, in the virtual memory. And now, because, you know, obviously because B is not actually in RAM anymore, well, then we can like load D into RAM. Right, now, for example, let's say, for example, I don't know, maybe we don't need C anymore, right, but we do need B. Well, then what we can do, of course, we can move C here into virtual memory, and, you know, this B can then be reloaded back, right, into C. So, yeah, I mean, basically what we're doing then is, well, we're just swapping. So, I mean, yeah, you can call this swapping, you can also call it paging, right, so like paging in, paging out. So, I mean, paging out is going to be, you know, moving from RAM into the, you know, virtual memory. And then, yeah, paging in, right, that's going to be, well, from virtual memory into RAM. So basically, we just want to explain this. So let's say maybe the, let's say secondary storage. Now, right, in the exam, okay, write this in paragraphs, but yeah, I'm going to be a bit quicker. Right, secondary storage can be partitioned. So partitioned, you know, just means split. Alright, partitioned into, I mean, let's say sort of normal area, or I don't know, yeah, alright, well, let's say partitioned to allow some, you know, some space to be used as virtual memory. Alright, to allow, yeah, some, let's say some storage, right, to be used as virtual memory. Right, and then let's talk about this example, because they say page B is not needed immediately. Right, so let's say since page B is not needed, right, is, yeah, let's say currently not needed. Right, let's say it can be paged out of RAM, or you can say swapped. Right, so it can be, yeah, let's go swapped. Or in fact, well, let's go paged out, because I mean, paged out is more specific in saying, yeah, is it sort of outgoing or is it, coming in? Right, so it can be paged out of RAM, right, and placed in virtual memory. Right, okay, let's say this creates room. Right, okay, yeah, this creates maybe space in RAM. Right, for page D to be loaded in. Yeah, okay. Right, and then I think then we can mention, I don't know, we can maybe mention this process is ongoing. Right, yeah, this process is ongoing. And then we'll say, when B is needed again. Let's say, right, e.g., if A is not needed. Right, so if A is not needed, but B is, yeah, but page B is. Right, then we can swap page out, or, well, we can say, yeah, then we can swap page A into virtual memory and B back into RAM. Right, so swap page A, yeah, into virtual memory. Right, and page B back into RAM. Okay, and actually, I didn't explain, but let's just talk about what a page is. So in RAM, let's say you've got 16 gigabytes of RAM. Now, you don't want to think of the entire thing as being, like an entire 16 gigabytes. What they do is, well, they break it down into pages. And I think usually, at least on Windows or on my computer, each page is going to be 4 kilobytes. So, because for example, like you don't want to like load in the, well, let's say if we're using virtual memory, like we don't want to page out the entire program, because if we've got some big program, I don't know, maybe Photoshop or some game, or some like 3D rendering software or something, this can also be like gigabytes upon gigabytes. So moving that entire thing into virtual memory, right, that's going to be slow. But for example, let's say we only need, I don't know, maybe 100 megabytes, to be removed. Well, then of course we just remove, 100 megabytes worth of these 4 kilobyte pages. So yeah, that's kind of one reason why paging is used. Right, software is installed on a computer to manage files, memory, and multitasking. State the name of this software that can do these tasks. Right, so that's just going to be the operating system. Because yeah, these are like file management, memory management, I guess multitasking. You can also think things like security management, right? It's going to provide a user interface, yeah, things like that. Right, give one task that the software allows the user to do to manage files. Right, so I think here it's saying like, I don't know, let's say you go to your like Windows Explorer. Well, obviously you can create files, right? You can move files, copy. Yeah, delete, rename, right? Obviously, yeah, loads of things. Right, describe what is meant by managing memory. So I think what we can say is it's saying, well, we're going to allocate memory to a process when it needs it. So let's say we open, I don't know, a web browser, and let's say our web browser by default needs 500 megabytes of memory. Well, then basically, memory management is going to find 500 megabytes in RAM. And of course, like if required, it's going to have to page some things out possibly. So I think this is one thing, right? We can say so yeah, let's say maybe just allocates memory. We're allocating memory to processes that require it. You could, yeah, I guess you could mention that it's not just going to like infinitely allow memory, because let's say you have some process that wants like 100 gigabytes of memory. In that case, I guess it's just going to crash, right? Or maybe it's going to prevent the process from doing that. But right, let's go to processes that request it. Right, let's also say also. Right, so it's also going to ensure that two processes don't access the same memory, because if two processes kind of have overlapping RAM ranges, well then you can get it. Well, obviously, one process can modify another. Right, you get data corruption. You also get security vulnerabilities, because for example, well, they can read the data in that process. They can modify the instructions. Right, so let's say it also ensures that two processes don't have access to the same memory. Okay. And then, I mean, you could probably also talk about things like paging, segmentation. Now, if you want to see more about paging and segmentation, right there's a video I always recommend. I mean, this guy, his channel is literally just called Computer Science. So if you just type in computer science paging and then segmentation, and I think so. Type in paging, segmentation, virtual memory, search that on YouTube, and I think it's like an 8-minute video. But I mean, this guy right here, I mean, he's got good videos. He explains it really well. A signal is sent within the computer to allow multitasking to occur. State the name of this type of signal. So I mean, this one is possibly a little tricky, because I think in the IG book, I mean, I'm not sure if they mention it, or if they do, they just do it briefly. But basically, it's going to be an interrupt. That's a U. And the way this works is, let's say we've got some process. I mean, basically here, this is going to be time. So it's just a time axis. So let's say this is process A, and basically each process will get a time slice. So I think usually a typical time slice is about, I don't know, maybe 10 to 100 milliseconds. I mean, let's keep it simple. Let's just say 100 milliseconds. So the processor will execute each process for 100 milliseconds. And then when that time is up, well, then an interrupt signal will be sent. And then what's going to happen is, well, then the next process will be loaded in. Well, then again, that's going to execute for another 100 milliseconds. Again, there's going to be another interrupt. So that process is going to stop. Of course, the next one, let's say C. And then, I mean, I don't know, maybe then it's going to go back to A. And I mean, this algorithm, you can also just call this round robin. I mean, this is more kind of A-level. So that's going to be called round robin scheduling, which people can look up if they want to. But the key point is that, again, when the 100 milliseconds is up, or well, when the time slice is up, when the time slice is up, an interrupt is going to be sent. Basically, I mean, what's going to happen, it's going to save the contents of the registers. And the reason it saves the contents of the registers, so for example, the program counter, the MAR, MDR, CIR, things like the status registers, is because, well, when we load it back in, we want to we want to resume from the same place that we left off. So if we got to I don't know, instruction 1014, just some random number, then of course we want to resume from that same instruction. Likewise, we want to have the same data in the NDR, etc. Alright, anyway guys, I mean, I think that video went on super long, but hopefully this is useful, and if it is, well, see you again in the next video.